Okay, welcome to part 3. So, in the second part, we had introduced the idea of the variance of the Bernoulli distribution, and I made the argument that perhaps this is a better way to model the error of the decision trees. And I was saying, I also said that this is capturing the nonlinearity uh, in the decision tree. Um, or generally in any given process. So just a couple of terminologies that I'll introduce before we get to examining the variance. Um, we talked before about the first error rate, the misclassification rate, and how that's related to the absolute value function. And when you are measuring something using the absolute value function, that measurement that's related to the what's called the Manhattan distance. So I'll write this down. Let's grab the pen. And this is just a introduction to these terminologies that you may come across as you're studying decision tree or any kind of machine learning. I figure since we're passing through this area, we might as well introduce these terminologies. I won't go too I won't really go in depth with these terminologies, but the absolute value function that's related to what's called the Manhattan distance. Or what's called the L1 norm. And this variance right here is we see that it's related to the Euclidean distance. So variance, or the squared error, is related to the Euclidean distance. Or what's called the L2 norm. And how I think about that is these terminologies, they kind of make sense in the context in what we've discussed. I kind of think of it as the absolute value function. There's a Manhattan distance. So it's the what you typically see when you're studying this is you see that you have a point here. Well, so let's see here. You have a point here. You have a point here. You can only go through. You can only go straight lines, like as if you were in Manhattan. You can only go through. You can only go down, up or down, or left or right. Whereas this Euclidean distance, you can, if you have 2 points like this, you can go diagonally, whereas Manhattan distance you cannot. And this kind of makes sense in the context of what we had discussed. I kind of think of it as under the Manhattan distance, your error will be off. So let's say that you had a starting point. You had a starting point right here, and you can go. You're making some kind of forecast, so maybe it's like this. Well, under the Manhattan distance, maybe your forecast is slightly off. Maybe instead of this as the ending point, maybe maybe you have this as the ending point. So you're slightly off along this dimension right here. Whereas in the Euclidean distance, there's something that you haven't accounted for. So you initially have a starting point right here, let's say, and you make a forecast. So you forecast that you're going to end up here. This is a review of what we have talked about right here, but you actually end up over here, let's say. So hopefully that gave you some intuition as to the difference between the absolute value function and the variance. Okay, so with that out of the way, let's do the calculation and see whether using the variance function to our original problem, if that will actually help in distinguishing one decision tree from another. So if let's see here. So let's just remind ourselves what the decision tree originally looked like. So it's 400, 400, 300, 100, 100, 300. Okay, so let's start with A first. So we have the error rate And actually, let's graph the error rate. Let's see how it looks like. So if we graph variance, the error, and let's say this is the probability of class 1. Okay, so this is 1.0, this is 0.0, 0.0, and let's see what this is. Okay, and this is 0.5, let's say. Okay, so using this formula right here, if we have a 0.5 as the probability, then 0.5 minus 0.5 squared, so that's going to be 0.25 right here. Let's make this a little bit neater. Okay, and then how about at 1? So 1 minus 1 squared, well, that's going to be 1 minus 1, so that's going to be 0. Okay, same thing, 0 minus 0 squared, that's going to be 0. Okay, good. And then 0.75, and then 0.25. Okay, and I already worked this out ahead of time, so that's going to be 0.18. Here, let's 0.1875. And that's going to be for both of these guys right here. So this is going to be a curve. Hence all this discussion about nonlinearity. Okay, so now let's do the calculation. So if we do the calculation, let's see here. So for the first decision tree, we have the variance of the parent of A. So, and we saw that it was 400 and 400, so that's going to be 0.5 minus 0.5 squared. So that's going to be 0.25. Okay. And then what about the child node? So we have the variance of child 1 of A. Let's see here. And we took the majority class before as our reference, so we could do the same thing. So it's 300 over 100. So then the probability of this class, of this whole thing, would be 0.75. Okay, running out of room. Let's see here. Oops. Okay, so that's going to be 0.75 minus 0.75 squared is equal to, what did I have? I wrote this down before. It's going to be 0.1875. Yep. And then for the child 2, oops. Child 2 of A is equal to, it's going to be the same thing, so it's going to be 0.75 minus 0.75 squared, so that's going to be 0.1875, same as this. Okay, so then what's the, let's take the weighted average of these two child nodes. So we said before that each node had 400 out of the 800 from the parent, so it's going to be 400 divided by 800 times 0.1875 plus 400 divided by 800 times 0.18, oops, 175. Okay, so then that's just going to be 0.1875. Okay, cool. How about B? All right, this is our grand finale moment. So for B, that's going to be what? It's going to be variance of the parent of B is equal to, well, this part is going to be the same, so it's going to be 0.5 minus 0.5 squared, 0.25. And then the child, it's going to be variance of the child 1 of B is going to be, all right, what's the majority class? What's the majority class of B again? Oh, majority class was 400 over 200 and 200. Okay, So then so 400 over 200, so it's going to be 4 over 6. Oops, so let's do it like 4 over 6, or 2/3. Let's do it as 2/3. 2/3 minus 2/3 squared. And I had already worked this out ahead of time. That's going to be 0.2 to repeating. And then how about the variance of the child of the second node? Child 2 of B, so that's going to be, let's see here, 200 over 200. So 200 divided by 200, that's just going to be 1, minus 200 over 200, and we're going to square the whole thing. So that's 1 minus 1, so that's just going to be 0. Okay, so then let's see what's the weighted average of this guy, of these two children node. So for the first node, recall that we had 600 that went into the first child. So if we scroll back up here, so we had 600 in this node, and we have 200 in this node. So those are going to be the weights. So let's, oops. So grab this. Okay, so it's going to be 600. Let's this thinner. Oops. Okay, so it's going to be 600 divided by 800 times this guy right here. So it's going to be 0.22. Oops. 222 repeating, plus 200 over 800 times this guy right here. So that's going to be 0. Okay, so then, and I had already worked this out ahead of time, so then this is going to be 0.1666 repeating. And this guy is less than this guy. All right, cool. All right, awesome. So it did turn out that this contrived example worked out as nicely as we thought it would, of course. So yes, incorporating nonlinearity did help with distinguishing between one decision tree versus another. And just one more concept that I'll introduce but not discuss in detail before I wrap up. So what's going on right here? Let's see here. So what's going on right here? So we are taking, we are using this function right here, and we are, let's see here, we are taking 0.2. Let me just draw this over here. So if I draw this right here, so we had 1 right here, we had 0.0 right here, 0.5, and okay, so we started out right here at 0.25. So we started out right here, and then we ended up with weights like this. Okay, so we had a weight right here, and then we had a weight at 0.22 repeating. So let's say that this is 0.22 repeating. So we had another weight right here. So this was the, let's see here, let me mark this. This was the parent node, the error of the parent node, and then let's see here, let's mark this as, this was the child node for this guy right here, and then let's use purple. This was the child node for this guy right here. So then what did we do? We basically took these 2 points and we drew a line, and we took a combination, a an average of these 2 points right here, and we end up with a value at around here. And we end up at a value at around 0.1666 repeating. And this, so notice that this point right here is smaller than the corresponding point on the curve. So let's say it's this guy right here. Yeah, let's say it's that guy right there. And this guy, this relationship between this linear this line right here and this curve right here, this is called Jensen's inequality. And let's write this down, Jensen's inequality. Okay, so I just wanted to introduce that term, but in the future I will do a video on Jensen's inequality. So hopefully this gave you some intuition on the difference between the absolute value and the variance.